Good morning, ladies and gentlemen. So I just want to tell you that today you better buckle up because we are in for a treat. By treat, I mean it's going to be a little bit of a doozy, but we're going to get through it together, so don't you worry, okay? So today we're going to talk about graphing sine and cosine. And the graph of the sine function, what we're going to do is we're first going to complete the xy chart over here to the left by listing the corresponding radian measure and degree measure. Then we're going to strategically select angles or inputs that have a rational output value. Then we're going to determine the y value, and we're going to notice to see if the pattern continues while graphing until the entire grid is filled. We're going to use the unit circle right below to help us complete the table. So the first thing I want to do is I want to try to find some important points. And I'm going to start with degrees first because I know everybody here loves degrees. So what I'm going to do is I'm going to start at 90 degrees because at 90 degrees, sine is 1. And if you guys don't remember this, remember cosine is the x value and sine is the y value. Okay, so we're looking at the y values when we're talking about a graph of sine of x. Okay, so we have at 90 degrees, it's equal to 1. That would be our output. So sine of 90 degrees is 1. Okay, so, and if I look, every time I go 90 degrees, I get another value that's really easy to graph. So let's do that. So we have 180 next, then we have 270, and then we have 360, and then another 90 is going to be 450, and then 540. Okay, so sine of 180 is 0, sine of 270 is -1, sine of 360 is 0, sine of 450 is 1, and sine of 540 is again 0. So hopefully you're seeing a small pattern here. Oh, and we have sine of 0, which is also 0. Okay, so we're actually going to go in the negative direction next. So now we have -90, -180, -270, -360, -450, -540. Okay, and if we actually continue this pattern, we have 0, 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, -1, 0. Now you guys could check these by going around the unit circle, but if we see the pattern, we can definitely use the pattern. So I left radians a little bit but to the end here because I know that you guys often suffer when looking at radians, but that's okay because we're going to do it together again. We have pi over 2, then we have pi for 180, then 3 pi over 2, and then 2 pi, and then 5 pi over 2, and then 3 pi. Now in the negative direction, you have pi over 2, negative pi, -3 pi over 2. My pi's are getting worse and worse as I go, so -2 pi. Then we have -5 pi over 2, and then -3 pi. Now you guys might be asking yourselves, okay, so we have this chart filled in. What we're going to do is we're going to use this now to graph sine for the very first time. Okay, now I kind of copied this over from the other page. I cheated a little bit because we couldn't go back. So we see that this line right here is pi over 6, which means each one of these lines is pi over 6, which makes this right here pi over 2, which means every 3 is another pi over 2. Okay, so this is going to be pi. This is going to be 3 pi over 2, and then we have 2 pi, and then we have 5 pi over 2, and then we have 3 pi. In the opposite direction, we have -pi over 2, and then we have -pi. Then we have -3 pi over 2. Then we have -2 pi, -5 pi over 2, and then we have 1, 2, 3, -3 pi. Okay, so now that I have my graph all set up, I can now graph these points that I have over here. So we know that at 0, the y value is also 0. So when x is 0, y is equal to 0. Okay, so we have it going through the origin. So next we have 90 degrees, or pi over 2, which is at 1. At pi, we go back down to 0. At 3 pi over 2, we go all the way down to -1. At 2 pi, we're at 0. At 5 pi over 2, we are back up at 1, and at 3 pi, we're back down to 0. And we can actually continue to plot these points here. I think you guys see a pattern. Just make sure I don't mess up the pattern. Okay, now you might be wanting to draw a line through these, but a sine graph is actually a sinusoidal graph. So what does that mean? We're going to draw a smooth curve, or as smooth as we possibly can, through all of these points, and then we'll have sine. So I'm going to start over here just because I can. I'm going to come down, up, down. As you can see, this is not perfect, but we're trying our best here. Great. Now it doesn't stop at 3 pi or negative 3 pi. It actually continues going on forever. Okay, we could keep going around these graphs just like we could continue to find coterminal angles here. But now that we have sine, a graph of sine, we can actually start thinking about other things like domain and range. So if you look at the domain, remember that domain is the x values, and we just talked about how those continue in both directions. So we can actually say that the domain is all real numbers. This is the symbol for all real numbers. But if you guys don't remember the symbol, that's okay. It's also from negative infinity to positive infinity. Before you guys go making fun of my infinities, I can't draw a sideways 8 to save my life. So that's how I draw them, okay? So this is all real numbers in the domain. But if we look at the range, our lowest number is at -1, and our highest number is at +1. And it's inclusive on both ends. So it's inclusive from -1 to +1. Okay. Another thing we can talk about, zoomed in a little bit too much there, is the period. And a period is a length of one full cycle in a sine or cosine or actually any trigonometric function. So I like to start here at 0 because I know I can control it. So we go up, and then we go down, and then we come back up. Let's see if I can get a different color real quick. Oh dear. Wow, we went very far ahead here. Spoiler alert. Okay, so I can't get a different color, but if I'll try to make it bolder here. We're going up, and then we're going down, and then we're back to the same spot. So you can actually take these, and you could copy paste over and over and over again, and it'll make this smooth curve. Okay, so how long does it take to repeat? It takes a distance of from 0 to 2 pi, so a total of 2 pi. Now, another thing we can talk about when we're talking about trigonometric graphs is the amplitude. And the amplitude is the height of the wave from the midline. So our x-axis here is actually our midline. So we're looking from the height from the midline to the maximum. Okay, and if you look there, that is a distance of 1. So my amplitude is equal to 1. And we'll be going over all of these definitions again and again and again. So don't think that you won't be able to understand it. You will, I promise. So this is actually sine. Now, we also have a cosine graph. Okay, and remember that it goes cosine, sine. This is our x and this is our y value. So when we're looking around the graphs, we're looking at these values right here. And why did I circle those values? Because we're going to use the same degrees in order to find our y's and x's here. So just copied from the other one because we've already done this once. We have these guys, and I'm going to go through this a little quicker. You guys can fill this out. I wonder if I can speed this up. I'm editing it. I guess we'll find out. Okay, we're getting somewhere here. So we have -360, -270, -180, -90, 90, 180, 270, 360, 450, 550. Okay, we filled out the whole graph. Now, what is different? So the x's are going to stay the same because those are what we're going to use in order to graph it. But however, the y's have changed, right? Because we're no longer looking at the y value of each point. We're looking at the x value of each point. So at 0, cosine is actually 1, which is different from sine because if you remember, sine at 0 was 0. At cosine at 0, it's 1. Okay, so let's keep going. Cosine at 90 degrees is equal to 0. Cosine at pi radians is -1. Cosine at 3 pi over 2 radians or 270 degrees is 0. Cosine at 360 degrees is again 1. And then I think you guys see the pattern again. Okay, so if we're going to go in the opposite direction, we have 0, negative 1, 0, 1, 0, negative 1. Okay, so we have now found all of the points that we need to graph on the cosine graph. So let's do that. Okay, again, cheated a little bit, I kind of copied and pasted here. So again, we have pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, and 3 pi. And I'm not going to mark them this time just for time's sake, but I'm going to go every 3 just so I know where to graph here. Okay, so we know that when x is 0, that means y is going to be equal to 1. So instead of going through the origin this time, cosine is actually going to go through 0, 1. Okay, it comes down to at 90 degrees or pi over 2 at 0, and then at pi, it's going to be at negative 1. Then it's going to go back up to 0, then back up to positive 1, and then back down to 0, and then back down to negative 1. And we're going to complete the same pattern on this other side here. Okay, so like sine, cosine is, we're going to draw a smooth curve through all of these points. We're not going to do a zigzag like this. I can't tell you how many times I see zigzags. Smooth curve. So we're going to start here. We're going to go up and down, up and down. Beautiful. Okay, so this is cosine. Again, the biggest thing is it looks a lot like sine, but one of the major differences, instead of going through the origin, this has actually been shifted a little bit to the right or left, depending on which way you want to look at it, and it now goes through 0, 1. I think that's one of the biggest factors on determining which one's sine and cosine between the two. Because you'll notice when we do all of this, they're going to be very similar answers because, again, our domain, it doesn't stop at these points. It continues on and on and on. So our domain is all real numbers, or it goes from negative infinity to positive infinity. Our range, again, starts at negative 1, goes to positive 1, and it's inclusive. So we have negative 1 to 1. The period, again, is a cycle. So we can start here at the y-axis, and we can go down. We go all the way down, and then we come all the way back up, and we've actually completed a full cycle at this point. So again, that's from 0 to 2 pi. That's from 0 to 2 pi here. So we have a period of 2 pi, and again, our amplitude is from the midline, which is, again, the x-axis. So it's going to come up and over, and that's also going to be 1. So when you're looking at the makings of cosine and sine, all of the things like domain, range, period, and amplitude are the same. The difference is where does it cross the y-axis? That is the biggest difference that you usually can find. Now, by the way, you can stop this at any time because if I'm going a little fast, you can slow it down. That's one of the beauties about videos. So we're going to note that the functions that behave in such a repetitive or cyclical manner are called sinusoids. Okay, the graphs of sine and cosine functions are also known as the sinusoidal wave graphs. Okay, so what we're going to do is we're going to do a couple examples. So we're going to describe the transformations that occurred to the parent function, y is equal to sine of x. Okay, so we're just looking at sine of x here, and I hope that you guys can bring some of your algebra 2 into the picture here, because we're going to do some transformations. Now, here the difference is this 2. Remember the parent function is y is equal to sine of x, so the difference in this function right here is that 2. Now, 2 in front of the function is stretching it in a vertical manner. So the answer here is that this is a vertical stretch by a factor of 2. Okay, by multiplying everything by 2, we're stretching all of the y values by 2. So we're stretching it in a vertical manner. Okay, so let's look at 64. We have 2 transformations here. We have this negative sign, which is its own transformation, And then we also have this 1/3. Okay, so what does the 1/3 do to it? Oop, we zoomed in a whole bunch again. So the 1/3, instead of, because it's less than 1/3 is less than 1, is not stretching it like the last one. It's actually going to shrink it. Or if you guys want to use more technical terms, it's a vertical compression. So I like shrink and stretch because I can spell those all the time. So it's going to be a vertical shrink by a factor of 1/3. Now, what does that negative sign do to everything? Now, that makes every positive y value negative and every negative y value positive. So what that's actually doing is it's flipping it over the x-axis. So that is a reflection over the x-axis. Okay, so those are our two transformations for number 64. Let's look at 65. So the difference in this one is this +1, but notice it's not on the outside of the function. It's being directly applied to that x value. So that means we're adding a number to every x value, adding 1, right? So we're actually, instead of going up or down here, this is actually going to be a horizontal shift. Hopefully, all of these transformations are coming back to you in a flash. If not, we can find some other things to help you guys out when remembering these. So the tricky part here is, and a lot of students get this wrong, is this is a positive sign. So a lot of people think positive means up or right. But in this case, the positive sign actually means that we're shifting to the left. We're shifting to the left 1 unit. And that is our whole transformation here. So in contrast to that, we have this in 66, we have this +2 on the outside of that x. So it's not being applied to the x directly, it's actually being applied to the y. So this is actually shifting up and down. So this is a vertical shift. And it's going to be up 2 units. Okay, so in 67, we have something a little bit different. We have something being multiplied to our x. So it's being directly multiplied to the x value. So what this is actually going to do, it's either going to shrink or compress. This is either going to expand or compress our entire function. It's like you're kind of pushing it in like an accordion. In this case, because it is greater than 1, it's actually a compression. So I like to think that when it's being applied directly to the x, it's kind of the opposite of what you would think. So because this is greater than 1, this is actually going to be a horizontal compression or shrink. Let's do shrink. Not going to risk spelling that wrong. By a factor of 2. So we're actually shrinking it in half, okay? And this last one here is we have sine of x over 4. Now, please note that if we're going to, we should probably rewrite this if we're going to be looking at it. So we have y is equal to sine of 1/4 times x. 1/4 times x is the same thing as x divided by 4. And by kind of writing like this, now we know that 1/4 is what our factor is going to be. Now, because this is less than 1, it's going to be a horizontal stretch. And we're going to be stretching it by a factor of 4. Okay. So again, these are some transformations. Hopefully you've brought this kind of made you remember a whole bunch of your Algebra 1 and 2 training on transformations. But hopefully you can just refer back to these notes if you do need help in that in the future. So then one of the things I definitely want to touch back upon is amplitude, because we kind of just grazed upon this. So the amplitude of sine of x and cosine of x is usually found right in front of the sine or cosine. So amplitude is denoted by an A, and it's always positive. So we always say that amplitude is the absolute value of whatever is in front of the sine or cosine. Amplitude is also known as the vertical stretch or shrink, okay? expansion, compression, whatever floats everybody's boats. Okay, so also a couple things. If A is greater than 1, it's going to be a vertical stretch. Oh, running out of space. Let's just rewrite this. If A is greater than 1, it's a vertical stretch by A. If A is less than 1, it's a vertical shrink by A. And if A is less than 0, it's a reflection over the x, over the x-axis. This is also, I believe, at the end of your notes. So you could write this down here just to remind yourself, but I believe it's at the end of your notes as well. So what we're going to do is we're going to do a couple examples, and the kids love these examples because I promise you they're not that hard. So what we're going to do is we're going to find the amplitude here. So we have y is equal to 3 cosine of x. Well, the amplitude is just the absolute value of a, and in this case, a is 3. So we have the absolute value of 3, which is 3. So the amplitude for 69 is 3. Okay, now we have y is equal to negative 4 sine of x, and we know that the amplitude is going to be the absolute value of negative 4, not 14, negative 4. So the amplitude is actually equal to positive 4. Okay, now in number 71, we have negative 1/2 cosine of x. So we know that the amplitude is going to be equal to the absolute value of negative 1/2. So that means the amplitude is going to be positive 1/2. And last but certainly not least, we have y is equal to 7.2 sine of x. Our a is 7.2. Maybe I should tell you guys the a's over here too. Boop. Just going to go back real quick. A is equal to 3. So our amplitude is going to be the absolute value of a, which is going to be the absolute value of 7.2, which is 7.2. Again, notice that all of the amplitudes are positive. Amplitudes are always positive. I cannot get this through enough. Okay, so I don't know what's going on over here with these graphs. Let's ignore that as best we can here. Okay, so we're going to find the amplitude of the graphs, and we're actually going to find the graph of the equation. So first of all, it doesn't even tell us if this is sine or cosine. But because this is going through the origin, and these are actually all going through the origin, I can kind of assume that all of these are sine graphs, all of these ones in red. Okay, all of the ones in the top, so 73 through 75. Okay, so now what we need to do is we need to measure the amplitude. And remember, the amplitude is half of the distance between the max and minimum, or from the midline to the maximum. So this is actually 1. So A, amplitude, is going to be equal to 1, which is right down here. Now, because this is looking like our typical sine graph, it goes up, we can also assume that it's going to be positive 1. So here we have y is equal to just sine of x, because the 1 is hidden. It's a super secret ninja 1. So this is actually our parent function of sine of x. And there's a reason why I put that there, because I want to make sure you guys see how it changes from one graph to the other. So in the next one, again, we know it's a sine graph because it goes through the origin here. And then we're going to be looking for the amplitude. Now, if you look, this one has an amplitude of 2. So the amplitude is 2. And because it goes up from the origin, we can assume that it's a positive 2. So A would also be equal to 2. So when we're writing this graph here, we now know that it's going to be A sine of x. So in this case, it's going to be 2 sine of x. Now in the last one, this looks a little different from the other ones. Okay, again, we know it's a sine graph because it goes to the origin here. But if you see, this actually goes down 2 from the origin. So our amplitude is still going to be 2, but our A, because it goes down, is actually going to be negative 2. This is actually a reflection of 74. So that means that our actual equation for this graph is going to be negative 2 sine of x. Okay. Now, if you guys look at 76 through 78, these do not go through the origins, okay? So we can assume that these are cosine functions. So if we start here, we're going to look for the a. We have from the midline to 1, it's 1. So our amplitude is going to be 1, and that also means because it's at positive 1, it crosses the y-axis at a positive number, that a is going to be positive 1. So this is actually cosine of x. 1 cosine of x. Okay? So let's look at the second one here. We have a is equal to 2. This distance right here is 2. It goes up to 2. It's a positive 2. So our amplitude is 2, and our graph would be 2 cosine of x. Now 78 is a little bit different from the other ones. If you see here, it actually goes down 2. So that distance is still 2, so our amplitude is 2. But because it is at a negative 2 instead of a positive 2, we can assume that this is a reflection over the x-axis. So it's a reflection of 77, so it's going to be negative 2 cosine of x. Okay, so here our a was actually negative 2. Now, hopefully I don't have any weird graphs all over the place. Okay, so what is the equation given? So if our amplitude is 4 and our function is sine, that means that we know that the a value is either positive or negative 4. Because remember, the amplitude is the absolute value of a. So a could be positive 4 or negative 4. Now, if I just asked for an equation, you guys could give me either one, but if I asked for all equations, I would need both. So we know that y is equal to a sine of x, so now we know that y is equal to plus or minus 4 sine of x. This right here is our answer. Now, if we look at 80, we know that our amplitude is 2, so this tells us that we have plus or minus 2, and our function is cosine. Okay, so we're looking at cosine, but then it gives us a point as well. So 0, negative 2. Okay, so this means it's crossing the y-axis at a negative point. So that actually tells us that this has to be negative 2. Okay, not positive or minus, it can only be negative 2. So that means our function is going to be y is equal to negative 2 cosine of x. Guys, I promise we're almost there. Okay, so let's talk about period. Now, period of you can write it as sine of bx, and y is equal to cosine of bx. So b actually determines what your period is. Depending on what b is, you're going to put it in one of these formulas. So whether you're looking for radians with 2 pi over b or degrees with 360 degrees over b. So period is also known as a horizontal shrink or stretch. Or again, remember you guys could have compression or expansion. So let's do an example, because period is one of the harder things in this section here. Oh, that was creative. Okay, so if you look at here, we have y is equal to cosine of x. The number in front of this x is 1, so b here is equal to 1. Okay, so let's do this in radians, just because I see it more often in radians. So we have 2 pi over b is our radian. So now we have 2 pi over 1. So our period is just 2 pi. Okay. Now if you look at number 82, our b is actually 4 here. So b is equal to 4. And we know that the period is 2 pi over b. So in this case, it's going to be 2 pi over 4, which reduced down, the period is going to be pi over 2. Now, this is actually a really good example of how the period affects whether it's going to be a horizontal shrink or stretch. Okay, because you see here, because b was 4 and that was greater than 1, we've actually gone from 2 pi to pi over 2. So we've actually shrunk our entire period, which you're going to see in the next couple of examples. Shouldn't get ahead of myself. Okay, so for number 83, b is equal to 3/2. Because we know that 2 pi over b is our period, we now have 2 pi divided by 3/2. Now what we're going to do here is we're going to keep, change, flip this fraction. Okay, so we're going to keep the numerator, So we have 2 pi. We're going to change the operation and we're going to flip the denominator. So now we're going to have 4 pi over 3. So our period here is 4 pi over 3. Make sure we're boxing all these. Okay, in our last example, we have 6x, so b is equal to 6. And we know that it's equal to 2 pi over b. So now we have 2 pi over 6, which means our period, when reduced, will be pi over 3. So finding period from an equation is not the hard part here. In fact, I hope everybody is able to do this part. What gets a little tricky is when you're looking at graphs. So let's look at these guys here. So at number 85, okay, what we're going to do is we're going to look at the number of cycles from 0 to 2 pi. And this will actually tell us what b is. It's a really cool trick that we figured out. So here's 0, here's 2 pi. And if you look at this, it has one cycle here, and then it has another cycle here. Okay, so this is telling us that b is equal to 2 because we have one cycle of pi, and then we have another cycle pi long. Okay, so we can do two things. We can see from the graph that our period here has a length of pi radians, or we could use our formula, remember 2 pi over b, to get 2 pi over 2, because it repeats twice within 0 to 2 pi, to just get pi. Either way is fine. Now, it wants to know what the equation is. Now, if you look here, the amplitude appears to be about 1. This also doesn't go through the origin, so I know that this is a cosine function. And because a is 1 and b is 2, we know that the actual equation is going to be cosine of 2x. Okay, so now let's look at number 86. So first thing we know here is that this goes through the origin, so we're looking at a sine function. Okay, how many cycles are from 0 to 2 pi? Well, if you look here, this is a complete cycle. In fact, from 0 to 2 pi, it doesn't complete a full cycle. It actually only completes a half of a cycle. There's only a half of a cycle from 0 to 2 pi. So that means that our b is actually 1/2. Okay, we can actually look at the graph to see that our full period actually takes 4 pi radians to complete. So our actual period is 4 pi. But let's say that you didn't want to look at the graph, you wanted to use you want to use what b was. You could do 2 pi divided by 1/2, which would be equal to 2 pi times keep, change, flip 2 over 1, which would again be 4 pi. So now we know what b is, we know what the period is. The period is 4 pi, and we know this is a sine graph. We also know that the amplitude is 1, and because this goes up, a is going to be positive 1. So our sine is actually, can be written as 1/2 x, because that's what our b is. Or you guys could also write sine of x over 2. Either way, I will take both answers. Okay, so let's put it all together now. Again, I know this is a lot. Okay, we're almost done. So what is the equation given? So 87, the amplitude is 1, the period is pi, and the function is sine. Okay, so what do we know from this? If the amplitude is 1, we know that a is equal to plus or minus 1, because again, we don't know if it goes up or down. It doesn't tell us if it has any other sort of transformation. We do know that the period is pi, so we know that 2 pi over b is equal to our period of pi. So we can actually solve this equation here to find out what b is. So that's what we're going to do now. Okay, so we're actually going to multiply both sides by b. So now we get 2 pi is equal to b times pi. We're going to divide both sides by pi to get rid of it. So now we get b is equal to 2. So now we know that a is equal to plus or minus 1, b is equal to 2. So now what we're going to do is we are going to put this all together. So now we have y is equal to plus or minus 1. We're going to keep out the 1, sine of 2x. Now, for number 88, we have an amplitude of 3. So we know that a is equal to plus or minus 3. We have a period of pi over 3, and our function is a cosine function. So again, we're going to solve for b the same way we did in the last one. So we know that 2 pi over b is equal to pi over 3. So we're going to solve for b here. So I'm actually going to multiply both sides. Oh, actually, I can cross multiply here. Don't have any other math teachers know that I just said cross multiply. So now we have b pi is equal to 6 pi, because 2 pi times 3 is 6 pi, which means that b is equal to 6. So now we have a, we have b, and we know it's a cosine function. So now we know that y is equal to plus or minus 3 cosine of 6x. Okay, now just for time and sanity's sake, we're just going to go over this real quick. So we've already talked about amplitude and period. Okay, we already talked about how if a is greater than 1, it's a stretch. If a is less than 1, it's a shrink, right? We also know that the period for sine and cosine is 2 pi over b. What we didn't talk about is something called a phase shift, and we also didn't talk about vertical shift. So if we're adding, let's just talk about vertical shift first because it's the simplest part. If we are adding a number to our overall thing, we're moving the whole graph up or down d units. Now, phase shift is where it gets a tiny bit more confusing. Okay, the phase shift can be found by finding what c over b is. If we are adding this, we are moving to the right. So if it's positive, it's going to the left, and if it's negative, it's going to the right. So how does the period affect the phase shift? Using the general form above, we can actually rewrite the function so you can see the horizontal stretch compression separate from the horizontal one. And that's what this is right here. And that's actually what this is. I formulated that from this actual part here. Now, you guys can use this at any time in order to solve the problems that are going to be coming up. Okay, so that is actually it for today. I know today was a long day, guys. I thank you for sticking with me if you watched the video. If you guys have any more questions or concerns, you can either email me or join me in the Google Meets as always. If you don't have any questions, I hope you guys have a fantastic day.